Hi, I am Tom Christensen of Neurochrome. In this video, I will show you the performance of these power supplies here. They are Hanmatek HM310 and they are available for $80 at Bezos Bookstore. That is a screaming deal, or is it? We'll find out. I will be comparing them against these two HP 6643A power supplies that are available on the used market for $300 to $400 and up. The Hanmatek HM310 is a 310 watt power supply. The main output here provides 0 to 30 volts at up to 0 to 10 amps for a total of 300 watts. The remaining 10 watts come from this USB output here that provides 5 volts at 2 amps. And the first thing that comes to mind is that this is tiny. I mean, it's barely bigger than a couple of books stacked together. And it is light. It is 1.5 kilograms. So it's clearly a switching power supply because there's no way you could fit a transformer in there within that weight limit. So anyway, let's crack this one open and see what it looks like on the inside. There's some no-name Chinese capacitors, a current shunt, probably for monitoring the output current, some transformers. Interestingly, one of them has this funky flyby lead here. That's kind of curious. I'm guessing they did that to meet creepage or insulation standards. I'm guessing it's a resonant design based on this polypropylene capacitor here. Also note that there's a separate supply for the USB. That's probably just off-the-shelf part that they bought and stuck in there. The circuit board is, I mean, the assembly quality is kind of okay-ish. There's hot glue in a couple of places, but it's not fantastic, I would say. But it's about, I mean, for 80 bucks, that's about what I would expect. The biggest concern I have is this attempt at making a heatsink here. It's basically a stamped piece of aluminum that has the power devices mounted to it. There is a thermistor back here that keeps an eye on the temperature. And it's fan cooled with this fan back here, but I highly doubt that this is going to be very efficient. And if this power supply is supposed to be able to deliver 300 watts, then I would expect somewhere around 45 watts to be dissipated in these devices. And I doubt that'll make it, but I guess we'll find out. I'll torture test it later. Now flipping it over to the back side, we can see that the company didn't really want to spend on thicker copper, so instead what they did was they made openings in the solder mask so that when the board went through wave soldering, it picked up a bunch of solder. But I mean, it's way thicker here and here than it is here, for example. So I mean, they didn't do a fantastic job with this. It's also coated in flux down here. It's probably no clean flux, but I mean, this doesn't exactly scream quality, but on the other hand, $80 doesn't exactly scream quality either. Maybe you get for what you pay for, maybe you get more. We'll find out. And up against the front panel, there is a circuit board that has some, it looks like a switching power supply and also a microcontroller and some other chips on it. I'm guessing the switching power supply creates 3.3 volts for the micro. That's kind of a curious choice, but whatever. That's what they chose to do. On the front panel here, we have a pair of encoders. They actually feel pretty good. They do have a switch that barely has any travel, but it is there. The output jacks are pretty small, and I'm kind of curious if they will actually survive the full 10 amp output current. And then there's a push button power switch. On the back side of this thing is the IAC inlet, fan exhaust, and then a power switch. The standard spacing for binding posts on test equipment is 3/4 of an inch or 19.05 millimeters. Unfortunately, Hanmatek had to be different. The binding posts are a little bit further than 3/4 of an inch apart, and that means you cannot use a standard banana plug adapter. Now let's turn this thing on. Ta-da! There you have it. It basically boots up, checks that the fan is working, and then turns the fan off. And that's actually pretty nice. I appreciate that I don't have to listen to that the whole time. To set the output voltage, you push the encoder and you then get to change the output voltage 10 millivolts at a time. Unfortunately, the encoder doesn't really have any sort of acceleration on it, and it's actually fairly slowly responding. So you kind of have to be slow and deliberate when you adjust it. And thankfully, you can actually push multiple times and you get to select which digit that you want to change. So now we're cooking with gas, like that. And similar for the current, if you push the current encoder, then you get to change the current 1 milliamp at a time, and you can select which digit you want to change. It's a bit unfortunate that the supply times out so quickly. Now for the test of the power supply with no load. So I have the supply configured for 30 volts at 2 amps current limit, and at 30 volt setting it provides 30.026 volts, so it is off by 27 millivolts. That's not too bad. That's 0.1% if my math is right, so not horrible. Let's see what happens if we change by 100 millivolts, and for each 100 millivolt step I change the output voltage with 100 millivolts. And let's see with the 1 volt step. Oh, the fast timeout here really comes into play because the meter barely settles before it times out. So that's actually kind of annoying. There you go. It happens quite a bit that when I troubleshoot or prototype circuits that I look at the variation in some performance variable as function of power supply, and I like to be able to at least tweak it. But here, I mean, you really have to be on the ball if you want to be able to there it goes again. If you want to be able to make any settings before the power supply is timed out. That's a little bit unfortunate, but the readout precision does appear to be pretty good. It's within 0.1%. And if I change it by 10 millivolts on the display on the front panel, it changes the output by 10 millivolts and so on. So life is good there. No reason to belabor that point. Let's now turn the output off and then switch to the current measurement. And now, when the supply provides 2.000 amps according to the display on the front, it provides 2.005 amps according to the multimeter. So that's actually pretty darn good. That's what, 0.02% or something like that. So that's pretty good, especially for an $80 supply. It is important that the output voltage of the power supply ramps up gradually and without tendency to overshoot when the power supply is turned on. Otherwise, you run the risk of frying the circuit that's connected to the power supply. So let's look at the output of the power supply with an oscilloscope. I have the supply configured for 30 volts and the supply loaded with a 16 ohm resistor. Let's have a look at the output voltage as the supply is turned on. Like that. And as you can see, it ramps up gradually without tendency to overshoot. That's fantastic. Let's just double check at a lower voltage. So I will reduce the output voltage of the supply to 3.3 volt and run this test one more time. And as we can see, it ramps up without tendency to overshoot. It just settles at 3.3 volts and life is great. Let's run the same test for the constant current mode. I have the power supply configured for 30 volts and 2 amps current limit. I have it loaded with 8 ohms, so when I turn this power supply on, its output voltage should settle at 16 volts. Power on, and as you can see, the supply voltage ramps up until it hits about 10% above the current limit, and then there's a bit of undershoot before it settles at the final voltage. And that's not fantastic. It's not horrible either. A 10% overshoot is probably not going to kill your part, but this is definitely something to be aware of if you're trying to use this as a current source. It is of course important that the power supply also delivers the correct output voltage when under load. So that's what this static load test is for. I have the power supply configured for 24 volts with a 6.1 amp current limit, and I have the electronic load, which is a BK Precision 8600B, configured to draw 6 amps. The load is limited to 150 watts, and 24 times 6 amps is 144 watts. With no load, the power supply delivers 24.021 volts on the output. And when I turn the load on, the power supply voltage drops by 60-70 millivolts, give or take. In fact, let's use the null mode to do the math for us. And it looks like it drops 53.5 millivolts. So this isn't as good as the HP, that's no surprise there, but it's still, this should be pretty capable. And now for the dynamic load test, and this is intended to mimic the load current of a class AB output stage. That is why I have chosen the 60 milliamps for half of the cycle and 3.75 amps for the other half of the cycle. And as you can see on the scope, well, it looks like when the load drops, then this power supply stabilizes pretty quickly. But when the load increases, the load current increases, then it rings quite a while. And it's actually not done ringing, so I think I will change this to 100 hertz and remeasure. Oh wow. So as I suspected, the ringing actually takes quite a while to die out. Notice that I changed the time scale on the scope, so this is actually 100 hertz. And not only is there a significant spike when the load drops, it also takes quite a while for the power supply to discharge to the correct voltage. And I've actually seen that when I've turned the power supply off just with the multimeter connected, it takes a few seconds, maybe 10-15 seconds for it to discharge completely. So unlike the HP power supply, and also unlike the B&K power supply, there's no load in this to draw the output down when you turn it off. That's why you see this sort of behavior. And also notice that when the load current increases, then there's a significant amount of ringing on the power supply. So this is not a super stable design. And now for the test of these power supplies with the audio amplifier. The amplifier is based on the LM3886 by Texas Instruments. It is your prototypical audio class AB power amplifier. As you can see, the audio amplifier provides 40 watts into 8 ohms. As you also notice, the distortion is quite a bit higher than it was with the HP power supplies. Let's tease out what's going on here. One reason is obviously all this mains hum here. I did spend quite a while trying to figure out the cause of that, and I have reached the conclusion that it has something to do with the power supplies themselves. I mean, first off, because this is the exact same setup as with the HP power supplies, but also sometimes with switching power supplies, especially if they're not optimized for audio, the EMI filter on the input can cause leakage of 60 Hz into the output, and that might be what's going on here. Now let's take a look at the distortion sweep. So it's no surprise that the distortion starts out quite a bit higher here. And that is, as I mentioned, in part because of that mains hum, but we'll see if there are other reasons. I mean, this is obviously not impressive. This is way worse than with the HP power supply, and the difference between these traces is all due to the power supply. So let's take a look at the FFT and see if there's anything in the spectrum that would indicate what's going on here. And this is fairly obvious, or that stands out to me immediately for sure. That along with the mains hum. And this right here at 55 kilohertz is the switching frequency of the power supply. So I bet if we remeasure with 40 kilohertz measurement bandwidth, we'll knock all that stuff off. Okay, so that's better. This difference here is due to the removal of the switching frequency and the associated noise. But this difference here has got to be due to the mains hum and or other power supply deficiencies or differences. And this is a bit curious, but it looks like it bottoms out right at 60 hertz, so that could be related to the mains hum as well. And let's just let the sweep finish. So this, I mean, both of these measurements with the HM310 are way worse than with the HP power supplies. So this power supply is not really suitable for audio work. Now let's take a look at the output voltage of the power supply on the oscilloscope. The supply still feeds the audio amp, which provides 40 watts into 8 ohms. And you can see the output current of the power supply in green. And also you can see the output voltage in yellow. You can see the switching hash a little bit riding on this waveform. And also the waveform seems to be bouncing up and down a little bit. And I'm thinking that's probably the 60 hertz. That aside, it actually doesn't look too bad. And not that much different from the output of the HP power supply. So I'm a bit surprised that the distortion measurements are so bad. Now, in case you haven't noticed, precision is a really big deal to me. So when I say something doesn't work all that well, I do want to be right about it, or at least be able to back my claims up with measurements. And it therefore bothered me then when I, a couple of days after taking these measurements, took more measurements with the Hanmatek power supplies, but this time powering this Neurochrome Universal Buffer preamp, and found that it actually performed pretty well. I really started scratching my head and wondering, maybe I missed something. So I actually found one way to improve the measurements with the Hanmatek power supplies and the LM3886 power amp. And what I found was if I take this common ground point, and connect it to the frame ground of the audio precision analyzer, the distortion gets quite a bit better because the mains hum gets drastically reduced, as we can see here. So now what we see is that all of the mains hum that was there before is now basically gone. There's probably a little bit left, no big deal. So let's take a look at the distortion sweep. And as you can see, the distortion is practically line on line, maybe even slightly better at high frequencies. And that's pretty cool. That's definitely encouraging. Now it starts to break down again, and that's kind of curious, but this does support my theory that it has something to do with the EMC filter in this power supply that injects noise into the ground, and that noise ends up making it into the audio analyzer. And then by connecting the ground or common point of this circuit to the frame ground with a beefier wire, most of that noise current now flows in this wire and the measurement is improved. But this is still not good enough, at least not for my taste, and it's not like the LM3886 is a super duper high performance amplifier like the Modulus 86, for example. So I would still like to get better performance out of this setup. So I tried a few things trying to get to the bottom of this, and I'm not really able to find a good solution, at least not one that makes these power supplies perform as well as the HP power supply. What I did find is that if we add one more grounding wire from the common point to the analyzer frame ground, the results get a little bit better. So we can see here the results are practically line on line with before, and then there's a slight improvement as the frequency is swept past 200 hertz. So, I mean, there is something going on that's related to that error current that flows between the ground of the power supply and the ground of the analyzer. And that's a bit unfortunate. That's actually a very common issue with switching power supplies and PC power supplies, that they tend to inject a little bit of error current into the ground. That's not something I have control over. That's something that's inherent to these power supplies. So I would say close, but no cigar. But I mean, if you're running an electroplating system, these are probably fine. But for audio work, I would look someplace else. And now for the fun part of the show. At least I hope we get to blow this up. That's my plan. I am just trying to hold the manufacturer to the specs that they promised when I bought it. And one of those specs was that it can deliver 10 amps of output current. And I kind of wonder how hot these output terminals get after a while of 10 amps. So that's the experiment I have set up here. The load will draw 10 amps, and the power supply will provide 1 volt with a 10.1 amp current limit. So, without further ado, let me turn the output on. Like that. And you might notice that the reading on the display here is quite a bit different from the reading of the display here. And that's the drop across the wires and also the banana plugs. Like I mentioned, they're not exactly fantastic connectors. But let's see. Well, anyway, we had about a foot of snow dumped on us last night, so I'll go shovel that and I'll come back in a bit. So it's been about 20 minutes now. The power supply is still going and it's still delivering 1 volt at 10 amps. And it seems to be running just fine. The fan has turned on, as you can hear. Every once in a while it'll cycle off and then come back after a few seconds later. And that's probably just the temperature sensor inside saying, hey, it's getting kind of cold now. So that's fine. And it also turns out that the binding posts are holding up just fine. I mean, they're not even warm to the touch. And if I measure their temperature with this IR thermometer, it comes in at about 27 degrees, and it's still ticking up a little bit, but I had expected a lot worse. So I think I withdraw my concern about the binding posts. My concern about whether this power supply can actually deliver 300 watts still stands, however, so let's check that out. For this part of the torture test, I have the output of the Hanmatek connected to my speaker dummy load. So that is a 4 ohm resistor that can handle 500 watts. Unfortunately, it's also fan cooled, so there will be a little bit more noise in here, but such is life. That 4 ohm resistor will draw about 7.5 amps from the power supply, and I need to draw a total of 10. So to pick up the slack, I have the electronic load configured such that the total load on the power supply is 300 watts. Let's power this puppy on and see how this goes. So that was the first part, and there you go, 300 watts. And I should probably turn the fan on those load resistors. So this might be one of those occasions where I get to eat my words, because I thought I was going to blow this up, and so far that hasn't happened. This supply has been delivering 300 watts for over 3 hours continuously now. It's done a wonderful job of heating up my lab, but it hasn't failed yet, and that's a good thing. That also means that the quality of these cheap supplies is getting a lot better, because I bought one about 10 years ago and that was pretty crappy. I mean, it wasn't the same brand, but same overall concept. So now after 3 hours, I mean, it is getting a bit lukewarm to the touch, and also the binding posts are getting a little warm. So if we look at the temperature of the binding posts, we'll find that it's now in the low 30s. And I mean, that's comfortable. And also, if we look at the exhaust air, we are finding temperatures sort of in the low to mid 30s. So, I mean, clearly it doesn't seem to be overheating. So overall, I would say that this power supply provides pretty decent performance. It's not great, but you also don't pay a lot. If you can live with the sort of quirky user interface that times out on you when you're trying to change the voltage, and you can live with the ground current that this seems to send through your audio circuits, then this might be a good option for you. So there you have it. Thank you for watching. If you liked the video, click like. And also, if you have suggestions on how I can improve these videos, drop them in the comments down below. I do read the comments, but I might take a while to respond. Thanks for watching. Have a great day.